This is the tic-tac-toe playing robotic arm project. The tic-tac-toe playing robotic arm system consists of a power system, a robotic arm controller, an image processing system, as well as a user interface that are combined to produce an interactive game of tic-tac-toe with an automatically or manually controlled robotic arm. The project aims to have a robotic arm which is able to play the tic-tac-toe against a human opponent by observing and analyzing the physical game board using a camera and image processing technology. The image processor watches for changes in the state of the physical game board and determines where new game pieces have appeared. Once a new piece has been detected, it sends the location of the piece to the user interface and artificial intelligence system where the digital game board is updated. The user interface system waits for input from a human user via the image processor, then uses the artificial intelligence portion to calculate the next move that the robotic arm should make. Once calculated, the AI sends the next moves back to the robotic arm control code where it controls the servos of the arm in order to place a new piece on the physical board. All of the code will be placed on one Raspberry Pi. Here you may see the system block diagram which shows the subsystem interactions. Once a new piece is placed by the human player has been detected by the image processor, it sends the location of the piece to the user interface and artificial intelligence system through the use of WebSockets implemented with Node.js and Socket.io JavaScript libraries. The artificial intelligence portion of the system calculates the next move that the robotic arm should make. Once calculated, the AI sends the next move results back to the robotic arm control using WebSockets. The current status of the subsystem is on the completion of integration and small details. The bulk of the socket integration has been completed, but it still needs to be tested with the other subsystems. As you can see on the game page of the AI UI system, there are a few options for the game levels that you want to play, either easy, medium, or hard. As you can see, we've set up the Node.js sockets over in the command line. From here, I can input a user move, which imitates what would be done by the image processor system. As you can see, as soon as I make the move, it displays the user move and the AI move and responds with the AI move on the board. This is what will eventually be sent to the robotic arm system. As you can see, another move has been made. This also displays within the console of the localhost browser. So this demonstrates that the moves will indeed be sent to the robotic arm system. You can see that the AI returns nearly instantly with a move after the human player has inputted a move into the socket server console, which is what we see in the command line. The row and column numbers are displayed at the bottom of the screen after each AI move, as well as in the browser console, indicating that the AI move has been sent to the socket client that will eventually be connected to the robot arm subsystem. You can also see that the winning states also function properly.
Hello, my name is Michael Feller, and I'm in charge of the image processing subsystem. The image processing subsystem waits to receive a go signal from the robot arm control subsystem. Then it takes a picture of the game field, performs image processing using hue transforms to find the game pieces and locations, and sends the data to the UI AI subsystem. The system is able to process a picture taken of a piece of paper with a board and pieces printed on it. It can do so successfully as long as no other large artifacts are placed on top of the board. The board must be oriented horizontally and vertically within 5 degrees. The X-shaped pieces cannot be placed horizontally and vertically, and the pieces must be placed inside the board sections. Here is an example input image from the Raspberry Pi camera. After applying edge detection, the system finds lines in the image, shown in green, and finds which lines are the board, shown in red. It then looks in each of the 9 sections of the board to see what piece, if any, is located there, shown in the red oval. Finally, it outputs the information to a JSON file for use by the AI UI subsystem.
This is the robotic arm control subsystem. The goal of this subsystem is to be able to control each servo in order to move the robot arm to any of the board positions in a smooth controlled manner. The main requirements of this subsystem is that the arm must be able to move to any position on the board in a quick, smooth manner given an acceptable movement command from the game AI. In its current state, the robot arm control subsystem exists as Python code written on a Raspberry Pi that is designed to communicate using I2C with the Adafruit PWM driver. The code consists of a loop that will wait for a movement command from the game AI and then searches for an appropriate function that contains the servo information to move to that position. The function that is called will contain a list of commands that will change the position of each servo in the arm in a specific order using the duty cycle calculated using the period of the pulse and the expected pulse lengths found in the data sheets of the servo. The robot arm control subsystem will be tested to see if it can move to all positions on the game board in a controlled manner. The subsystem will be given mock movement data from the command line of the Raspberry Pi. It will be then watched to see if its arm moves to the requested position within 10 seconds. The pass-fail criteria of this test is that robot arm must be able to move to each position on the game board quickly and without jitters. The importance of this test is to prove that the robot arm can actually move to any position on the game board. The smooth motion requirement will limit possible mistakes such as dropping the game piece and will make the robot look more professional. This is the arm control system functioning during its test. It is given movement command from the command line and then proceeds to the specified position. When complete, the robot will be holding a stamp that will press down on the game board to mark the space. Currently, the subsystem passes the speed requirement and the ability to move across all spaces on the board parts of the test, but it fails the controlled movement requirements as there is a ton of twitch movement in its motions. This is the power subsystem for the tic-tac-toe playing robot. The goal of this subsystem is to provide at least the minimum power necessary to run all electrical components when the robot is functioning at maximum load. This is done to ensure under all possible circumstances the project will function properly. The goal of this subsystem will be achieved using an AC to DC power transformer and a step-down buck converter. The power transformer will take the AC voltage from the wall out and convert it to a DC voltage. This is stepped down by the buck converter to around 5 volts to be used by the robotic arm and the Raspberry Pi microcontroller. Figure 1 shows the buck converter being designed for this project. The buck converter consists of a diode, inductor, capacitor, and power MOSFET. It steps down the input by turning the power MOSFET on and off. This in turn prevents the circuit from running a high current through itself at all times and also shrinks the input voltage based on the percentage the switch is on. In order to test the power supply subsystem, the buck converter circuit will be connected to a DC power supply with an output of 12 volts to replicate the output of the power transformer. In place of a load, a 1 ohm resistor will be connected to the output to achieve the 5 volt 5 amp output. This test is important because it proves that the subsystem can achieve its goal of being able to meet the power requirements of the project. As of the moment, the buck converter passes half of this test because it can produce the required 5 volt output as shown in figure 2, but is producing a negative 5 amp output as shown in figure 3. In the coming weeks, the issue with the design will be fixed and the circuit will be created on a breadboard.
Each subsystem has been designed and has a working preliminary build. The MATLAB image processing code has been converted to Python. The ARM is able to move to specified locations, and the AI UI subsystem is complete. We have also begun integration via working sockets and reading and writing JSON files. Remaining work includes refining subsystems, fully integrating all code onto a single Raspberry Pi with working sockets in the Python code, and making the PCB for the power subsystem. Instead of pieces being physical blocks, we have decided to use O and X shaped ink stamps. This way we do not have to worry about the arm dropping the piece in an odd area or shadows cast by the pieces. Furthermore, the power subsystem has been changed from a linear voltage regulator to a buck converter to increase overall efficiency of the system. Finally, we decided to use WebSockets instead of Unix sockets for simplicity.
The tic-tac-toe playing robot provides an excellent learning tool to students visiting Texas A&M campus on Aggieland Saturday. It's simple enough to visualize while also applying the concept of senior-level coursework that the university provides. It uses image processing to analyze the game board, servos to move the robotic arm, and a UI-AI interface to interact with the game.